Fellow workers, as Samuel Taylor Coleridge's poem, The Rime of the Ancient Mariner goes, water, water everywhere, nor a drop to drink. Do you think that has to be? Do you think it is? Well, Wellington Water, the council-controlled trading organisation that manages the supply of Wellington's water, does seem to believe that. Some of you may remember Mark Kinvig, who worked for Highways and Network Operations. He now is Group Manager, Network Strategy and Planning for Wellington Water Limited. About 2 weeks ago he put a post up on LinkedIn that discussed the future of the water strategy for Wellington, the 3 waters strategy. And with regard to drinking water, pointed out that in 30 years the Wellington region may have 80,000 more people, and thought that there would be a challenge. We might have to spend money on building a dam, another dam or two, $200 million. Of course, the other problem with dams is they're not environmentally great. And think of the problems of the world, the whole world problem of obtaining water. What about supplying the water needs of 10 billion people by the year 2050? You see, of the world's water, the world's surface, water covers 70%, but 97.5% of that water is actually salt water. Of the remaining 2.5%, only 0.3% is easily obtainable from lakes and rivers. So, is that a problem? Well, let's have a look at water itself. And much of what I have to say comes from Professor Marcia Barbosa, who is a theoretical physicist and has spent a number of years, about over 15 years, studying the properties of water. So let's do a little bit of chemistry. H2O, water, H2O. 2 hydrogens and an oxygen. So with the chemistry, you might remember from your chemistry that the second shell of electrons likes to have 8 electrons. So oxygen has 6 electrons, so it needs 2 more electrons. So it grabs an electron from the hydrogen here, another one from the hydrogen here, and they bond. These bonds are called covalent bonds. So, but it's not like this, it's more like this, 105 degrees apart. So, here we are, it's positive here and a positive here, and this is the trick of the oxygen atom, that's negative. And because it's like that, so you've got a negative charge there and a positive charge here. Because of that, water has 72 anomalous properties, and I'm just going to talk about 2 of them. The first is that the water molecule looks over here, and this hydrogen over here thinks it's a bit like here's the political candidate, and here's the political candidate's canvases. So they go rushing around. They like to shake hands, you know, they like to shake hands. Well, it's the same with the hydrogen bond. This bond here, these bonds here are covalent bonds. It's a bit like a very strong relationship between the candidate and the canvases. But Marcia Barbosa actually talks about these being like a marriage, but I'm not sure, because then the oxygen atom would have to be a bigamist. However, these canvases go around shaking hands. Marcia Barbosa says this is flirting, but anyway, they go around shaking hands, this one, that one, so they keep going around the different passing. So it's very easy to pass for molecules of water to pass one another. That's why water flows. But what happens under pressure? Well, I go shaking hands even faster. Isn't that great? Look, I've got more voters I can shake hands with. How do we apply that? Well, if you put water through a tube, a few thousandths of millionths of a millimetre thick, known as a nanotube, the water will flow 900 times faster. So suppose you've got some salt water. Now the salt water has the big sodium ion, and all these oxygen atoms in the water molecules go around the sodium ion. It's almost like all the candidates from one party, sticking to the sponsor, the big business sponsor. So all these other water atoms go speeding past. Oh, okay, see ya, along through that tube. So instead of boiling water and then condensing it, which is the usual method of desalinating seawater, you have a very low energy way of desalinating seawater. Another property of water, which is like this, with having the bipolar molecule, is that some materials love water, they're hydrophilic, and some materials hate water, they're hydrophobic. What if you're out in the desert? The Namibia beetle in the desert in Namibia. When it's hot air in the evening, it cools. The hydrophilic, it's got some tubes in its back. The hydrophilic surfaces attract the water molecules and they drop down and they hit a hydrophobic surface on the shell and it moves, and then the beetle tips itself over and drinks the water. If only we could use that same technique at scale, we could provide water to the people of the desert. And in fact, the ancient Peruvians did so. So, because of the properties of water, I say to Mark Kinvig, we don't have an albatross around our neck. Water, because there's water everywhere, there's a lot to drink. Thank you.